Let's talk about inequalities. If we have a statement like this, then that means that A is less than B. If we make a slight adjustment to this statement and make it look like this, then this means that A is less than or equal to B. So we say that this symbol here means less than, and this symbol here means less than or equal to. This statement means A is greater than B. And finally, this statement means that A is greater than or equal to B. So I could make this statement right here, and this is a true statement. It says that 3 is less than 5. Or if we turn this statement around in our head and look at it from another direction, we could say that this means 5 is greater than 3. If we write down this statement, that reads x is less than 2, and it means every real number that is less than 2. Now we could start making a list of all of the real numbers that are less than 2. But as you can see, there's no way to write every single number that is less than 2. So instead, we try to represent this inequality with a number line. So here's our number line with 0 in the middle, the negative numbers on the left, the positive numbers on the right. If we want to summarize every real number that is less than 2, what we would do is put an open circle around 2 and then shade in everything to the left. Again, we call this circle here an open circle, and this open circle indicates that this solution set in red does not include the number 2 in it, because this solution set represents x is less than 2 and the specific number 2 is not less than 2. Alright, let's look at another inequality. X is less than or equal to negative 1. If we draw out a number line, because we have a less than or equal sign on this inequality, we're going to use a closed circle at negative 1, and we're going to shade in everything to the left or less than negative 1. We used a closed circle here to indicate that negative 1 is included in the solution set, because negative 1 is less than or equal to negative 1. So in short, if there's an equal on the inequality, we'll use a closed circle, and if there's not an equal on the inequality, we'll use an open circle. Let's look at two more quick examples. X is greater than negative 3. Because we have a greater than sign and not an equal sign, we're going to use an open circle. And because this inequality says that x is greater than negative 3, we're going to shade in everything to the right. If we had x is greater than or equal to 1, we can draw a number line. We would use a closed circle at x equals 1 because of our equal sign in the inequality. And because of the greater than, we're going to shade everything to the right. Now we also have inequalities called compound inequalities. That would be something like this. This says that x is greater than or equal to negative 1 as well as x is less than 3. Now, I just think of this as x is between negative 1 and 3 because it physically is between negative 1 and 3 on the paper. And here is how we would draw this compound inequality solution. X has to be greater than or equal to negative 1, so we're going to use a closed circle at negative 1. X has to be greater than or equal to that, but x also has to be less than 3. So we're going to use an open circle at 3, and this compound inequality is represented by this piece of the number line right here. Okay, so those are the basics of inequalities. Let's now look at solving inequalities. The most basic inequality to solve might look something like this. And in this case, we just solve this inequality exactly like you would solve an equation. To get x by itself, we would need to subtract 3 from both sides because we're adding 3 to x. This plus 3 and this minus 3 cancel, leaving us just with an x on the left, and 7 minus 3 gives us 4 on the right. Graphing this inequality would mean we need an open circle at x equals 4, and x is greater than 4, so we're going to shade in everything to the right. Now, most of the time, solving inequalities is exactly like solving equations, but here's an example where we have to do one thing a little bit differently. If we have negative 6x is greater than or equal to 18, what we would need to do to isolate x is divide both sides of this equation by negative 6. That's because this x here is multiplied by negative 6, and we need to get rid of that multiplication. So on the left, x would be now isolated by itself. On the right, 18 divided by negative 6 is negative 3. But this is the only rule for solving inequalities that is different than solving equations. If we divide or multiply by a negative number, we need to switch the direction of the inequality. So up here we had a greater than or equal to sign. In the next line, because we divided by a negative number, we need a less than or equal sign. And that is our solution. If we wanted to graph that solution, we would have negative 3 over here. We would use a closed circle because we have an equal sign on this inequality, and we would shade everything to the left because it's a less than. Of course, solving linear inequalities can get as complex as solving linear equations. For example, if we had 2x minus 5 is greater than or equal to 7, we would need to do 2 steps. First, to start getting x by itself, we would need to add 5 to both sides. That would leave us with a 2x on the left after these two 5's canceled. On the right, we would end up with a 12. Then to get x by itself, we would need to divide both sides of the equation by 2, leaving us with an x is greater than or equal to 6. Again, if we wanted to graph that, because of the equal sign in the inequality, we would need a closed circle, and we would shade everything to the right because x is greater than or equal to 6. Now, just a couple more quick examples. If you had an inequality that looked like this, say if you have an x term on both the left and the right side of the inequality, you might correctly think that you want to get all of those x terms on one side of the inequality. To do that, you might think, okay, I'm going to subtract 3x from both sides. But that ends up doing something strange to this inequality. On the left, the 3x and the negative 3x cancel. On the right, the 3x and the negative 3x cancel. That just leaves you with 5 is less than or equal to 8. If we're solving along in an inequality like this and we get a true statement, just some statement that is always true, then what that means is every single x that we could possibly plug into this initial equation up here will satisfy this inequality. So we say that the solution to this inequality is all real numbers. No matter what x I pick to plug into this inequality, the inequality will always turn out to be a true statement. Now, if we wanted to graph this, we would just literally have to shade this entire graph from left to right. And that would be the solution set for this inequality. All right, one more example before I let you go. Let's say we have an inequality like this, and you might have the correct tick here to distribute this 2 through the parentheses. On the left side, then, we would get 2x plus 8, and on the right side, we would still have 2x plus 10. Now we're in a similar situation to last time. We have an x term on the left and the right side of the inequality. If we subtract off that 2x, 8 is greater than 10 is what we're left with. That is a false statement. What that tells us is that no matter what x we choose, we are not going to get a true statement from this inequality. So in the case where we get a false statement at the end of solving one of these problems, the answer for the inequality is no solution. If we wanted to graph no solution on a number line, well, it would just be an empty number line. There's nothing to shade in. Okay, well, I hope that gave you a good introduction to inequalities, and hopefully this will get you started on some of the homework problems. I'll see you next time.